Good morning. I'm Katie Cottingham, and welcome to this news briefing from the 251st National Meeting and Exposition of the American Chemical Society in San Diego. We're joined today by Dr. Gadhamshetty and Namita Shrestha from the South Dakota School of Mines and Technology. They will be talking to us about their work on generating electricity with tomato waste. So, Dr. Gadhamshetty?
Thank you, Katie. So, United States, it produces billions of kilograms of tomatoes every year, and state of Florida is a good example, the state which produces lots of tomatoes. And of course, tomatoes are delicious, we can all eat them. But the thing is, the reality is, these tomatoes, they go into the processing plants, and they prepare sauces, ketchups, and whatnot. And in that process, they generate lots of tomato waste. And another example or exemplary source of the tomato waste would be the agricultural produce itself. Once the farms start producing tomatoes, you'll have to produce literally some amount of defective tomatoes as well. So we have the defective tomatoes in the agricultural farms. We also have tomato waste coming from processing plants. And any chemical matter, as a matter of fact, it's endowed with chemical energy, and same thing goes with tomatoes as well as tomato waste. There's a lot of chemical energy sitting in there. So we just wanted to try out and see if we can use these waste tomatoes as source of electrons. Electrons would be analogous to chemical energy. And then we tried testing the defective tomatoes as the source of a fuel in a new electrochemical device. What it does is it takes the bacteria, the living organisms, and the living organisms, if they're happy, they're going to use these tomato wastes as the source of carbon, source of energy, source of vitamins, and source of micronutrients. And as we have anticipated, once we provided that kind of artificial environment in this electrochemical device, and once the bacteria was comfortable with the optimal conditions, so basically bacteria was happy in that artificial house, the bacteria has started degrading the tomato wastes. And it forms something like biofilm. It's a biological film, and it forms matte on the electrode surface. And in that process, it degrades tomato wastes, and then it extracts electrons out, and we have developed an electrical circuit which is going to pull the electrons out of the device. And that electricity could be put for a better use. So in summary, we found that tomato waste, due to its inherent characteristics, like it's rich in carbohydrates, it has a lot of redox active species like riboflavin, which is indigenous component of vitamin B2, and several other micronutrients. It could be a perfect fuel source for electricity production in the electrochemical device. And I'll let Namita Shrestha, she's one of the Ph.D. students. She's been working very hard to develop this technology, and she's going to say a few words about the research.
Thank you, Dr. Gadhamshetty. I'm really excited about this research. Dr. Gadhamshetty already mentioned about how it works and everything, so I'd like to add only a few points. Like, I come from a small country like Nepal, and we have power cut-off as high as 20 hours in a day. So this technology can be really helpful to the developing country like Nepal, and we cannot afford expensive technologies for waste treatment and all, and this is really inexpensive technology. So I'm really excited and looking forward for this research. Thank you.
Great. So do we have questions? Just remember to state your name and affiliation when you're asking the question.
So it's Kath O'Driscoll from Chemistry and Industry magazine. You mentioned that it actually works better with defective tomatoes, i.e. with the damaged tomatoes. Why is that?
Okay, so that's a great question. So the defective tomatoes, the United States Department of Agriculture, it has its own specification in terms of accepting the tomatoes or discarding the tomatoes. I'll give you one good example. One of the criteria for discarding the tomatoes is if it's not ripe enough. So it's just at its early stages of maturation, and during its early stages of maturation, it has already accumulated a lot of vitamins, micronutrients, and carbon sources, and that could be a perfect example on why the defective tomatoes could be an ideal source of fuel for electricity production. Yeah.
And also it mentions in the release, it talks about lycopene being important. I mean, why tomatoes and what's sort of special about lycopene?
Okay, so as a matter of fact, any plant, it participates in photosynthesis process. It takes sunlight, it produces whatever it wants. And same thing goes with tomatoes. It has its inherent capability to accumulate these natural pigments, and it goes back to its own survival mechanism. But summary would be it produces lycopene, and some of these pigments are the reason why the tomatoes are dark red or orange in color. And now if you discard these tomatoes or tomato waste, you are discarding those natural pigments, and they could be very useful for enhancing electrochemical reactions in these devices.
Could you just expand on that a little bit? How exactly, I mean, you mentioned it's a mediator. What does that mean? Okay,
so that's a great question. So what is the meaning of mediator? So these redox active compounds, some of these redox active compounds, and lycopene or vitamin B2 compound, they actually have a capability to go pick up electrons from some of the electron donors, and then they can act like shuttles. So they bring the electron from the electron donor, they take it back to the electrode, and once they get oxidized at the electrode, they come back to the source, they pick the electrons, and the cycle continues. And this is what can help these devices sustain higher current densities or higher electricity production on longer time scales and at higher current densities. So.
Yeah. And it says in the release as well that there's quite a low current produced at the moment. I'm just wondering, how high do you think you could get the current, and what are the sort of strategies to improve on the current that you're producing currently?
Okay, so that's a great question again. So what would be the strategies to improve the current densities in these devices? So, well, we have tested this concept in a laboratory scale, and the reactor configuration can be optimized. And if you could improve the physiological conditions, and if you could optimize the reactor configuration, choose the best materials in the world, theoretically 1 meter square of the electrode surface can produce nearly 7 watts of electricity. And if you translate that into volumetric power densities, you could take, let's say, a meter cube of water, and which would translate to 1,000 liters. You could produce nearly 1,000 watts. So, but those are theoretical limits, and we always have the practical challenges, and we are working to solve those challenges.
Okay, thank you.
Other questions? Yeah.
Becca Traeger with Chemistry World. You talked about this being inexpensive technology. Can you, either of you, elaborate on that?
Okay, so that's again a great question. Why would this particular technology be qualified as inexpensive technology? My answer would be simple. If you take any of the electricity producing technologies, you have to invest some source of high quality energy. For example, if you use power plants, you'll have to put in coal as the fuel, or you'll have to increase the temperatures to extremely high temperatures. But in this particular case, with this particular device, you are actually operating the device at room temperature, ambient conditions. You take the device, put it on the benchtop, it should be able to produce direct current electricity. That would be first reason. And second reason is there are no major investments on the kind of chemicals that are required to sustain the electricity production. And if you assume that defective tomatoes have no monetary value, instead of throwing them into the landfills, we can bring them into the device and use them as source of fuel. And with minimal water supplements, we should be able to produce electricity as we have seen in the lab.
What are the bacteria that are actually producing this transformation?
So that's a great question. I mean, microbial communities, they're amazing. For time being, we have used a mixed microbial population. So it's a mixture of microbial population that we have originally isolated them from sludge in the wastewater treatment plant. So in fact, the microbes are everywhere. So we are using indigenous sources of microbial populations. But that said, if you want to do more controlled experiments and investigate the electron transfer mechanisms on a fundamental scale, you can work with pure cultures. But for the practical aspects, you don't need pure cultures and so on.
I know a lot of other people are looking at municipal solid waste or other food waste to generate electricity in this way as well. I mean, could you just add in other waste to this mixture? Will it work with other things too?
Sure. Any kind of organic waste is endowed with chemical energy. You name it and you have it. Food waste, municipal waste, water, agricultural waste, tomato waste, everything is endowed with chemical energy. However, the degree of amenability with respect to each technology would vary. For example, in this particular case, we are talking about electricity production, you're talking about electron flow, and you want the media which would promote electron transport from one point to another point. So if that is the case, tomato wastes have been found useful, but that said, food waste could be an excellent source of electrons for this device. Yeah.
Thank you.
Other questions? Rebecca, we'll go to you, and then we'll go in the back.
Okay.
You said this has been tested on a lab scale. Can you talk more about what that involved?
Okay, so that's a great question. What did it involve for the laboratory scale testing? So basically, we work on really minuscule reactors, and the kind of reactor we operated was less than 100 milliliters, and probably 1 to 2 meter square of electrode surface, and then some of the pure chemicals for the counter electrode reactions, and then controlled current conditions. We have state-of-art potentiostats, which would allow us to maintain the electrodes at certain electrical potential. And therefore, we could actually manipulate microbial physiology to let it exit the electron at required, redox gradient and so on. So did I answer your question? Kind of. Okay. Okay.
Okay, we'll go in the back.
So thinking more long-term and with scaling up and everything, how do you imagine this will be applied in real life? So for example, would you have a tomato farm that collects its own tomato waste and then it uses the electricity generated from that waste to run the farm? Or do you envision this more on a larger scale? The press release mentions, this could run Disney World theoretically for 90 days or something. Do you imagine centralizing it and redistributing?
Sure. So that's a great question. So your question is related to the viability of using centralized versus decentralized facility for sustaining the tomato waste degradation and electricity generation. To answer that question, I'll go back to my example on the processing plants. You have the dedicated infrastructure where they're using the tomato waste on daily basis, and the tomato waste is being degraded, the tomatoes are being processed, and the waste is being generated. And there you have dedicated source of tomato waste sitting right at the processing plant. And that would be a perfect example. I mean, there's no limitation on the amount of feedstock you can get from the facility. So that could be one good example. Processing farms, that's still possible because no matter what kind of produce you're talking about, you'll have to sacrifice a certain proportion of the tomato produce on a daily basis or on a yearly basis. But again, that could be slightly complicated because the weather fluctuations would come into play, and also we might need dedicated manpower sitting there and trying to operate the fuel cells, operating the fuel cells. But that said, theoretically, it should be possible. And it might also, one day it might also be possible to go put one of my device right at bottom of my sink in the kitchen, and all of a sudden it starts producing electricity, and that's a possible, at least on theoretical basis. So.
Okay, other questions? What's next for your project and for your group? Where are you going with this?
All right. So for our group, we are always fascinated about using this electrochemistry, especially coupled with microbiology. The little critters, they do a fantastic job. So we are working along the lines of microbial electrochemistry, and there are several challenges that has to be addressed before taking this small-scale devices into the practical applications, and we are getting there. So we would like to address some of the material challenges, and also we would like to investigate some of the electron transfer mechanisms at fundamental scale, and do a lot more fundamental studies that would help transit the technology into practical applications.
Okay. If there aren't any more questions, then thank you very much for joining us. The archived version of this session will soon be posted at bit.ly/ACIUS Live San Diego. That wraps up our final press conference from the 251st National Meeting and Exposition of the American Chemical Society. Thank you very much for joining us.